Today we are going to be starting graphing tangent and all three reciprocal functions. I'm pretty sure I said it yesterday, but I can't remember, so I'll just go ahead and say it again today. The graphs of sine and cosine are a must-know. You must know them. In fact, if you don't know sine and cosine, secant and cosecant, just write them off. It would be like impossible. Now tangent and cotangent are completely different animals, so we'll start there. But then we're going to make our way into secant and cosecant, and I'll show you the way that I do these things. Recall, please, from way back in the day that tangent of x is sine x over cosine x. Everybody was cool with that, right? Because it's y over x. Okay, well, what that means is tangent of x is going to be equal to 0 every time the top of that fraction equals 0. So every time sine of x is 0, tangent of x is 0. But that also means that the denominator could be 0, and you can't divide by 0. So that means tangent is undefined when cosine is 0. That means tangent has an infinite number of vertical asymptotes because cosine is going to be undefined, or excuse me, is going to be equal to 0 often. So when will the zeros occur? Well, let's see. Sine, which is y over r, or just y in the unit circle, will only be 0 if y is 0. And y equaling 0 implies that we're on the x-axis. So 0, pi, 2 pi, 3 pi, 4 pi, so on and so forth. Our zeros occur at all of the integer values of pi. All the integer values of pi. Now cosine is x. So in order for cosine to be 0, you need your x coordinate to be 0, which implies you're on the y-axis in our unit circle. So pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, all of the odd multiples of pi over 2. So you have more than one way of thinking about this. But if you remember back to when we were talking about the ASTC stuff, when is this positive, all, sine, tangent, cosine? Or maybe when we were evaluating trigonometry, we talked about periodicity. Sine and cosine have periods of 2 pi. Tangent has a period of pi, though. It's positive in quadrant 1, negative in quadrant 2. And then it repeats with 3 and 4. So it has a period of single pi. All right. Let's put asymptotes at all of the odd multiples of pi. Over 2, excuse me. Odd multiples of pi over 2. Sorry. And zeros at all of the integer multiples of pi. Quadrant 1 is from 0 to pi over 2. In quadrant 1, tangent is positive. So from here to here, all of my y values have to be positive. And this is a vertical asymptote, also known as an infinite discontinuity. That means that my graph is going to have to stay above the x-axis, get infinitely close to this, and shoot to one of the infinities. It really doesn't have a choice but to do that. Now quadrant 2 is from pi over 2 to pi. In quadrant 2, because our x values are negative, tangent is negative. So I have to stay below the x-axis, get infinitely close to this line, and, because it's an infinite discontinuity, shoot to an infinity. It really doesn't have a choice but to do this. Quadrant 3 is a copy of quadrant 1. And quadrant 4 is a copy of quadrant 2. I think you get the idea. There's your tangent function. Notice that there's exactly pi between the zeros. There's exactly pi between the asymptotes. That's because pi is the period. So when you're working on graphing these things and you're trying to figure out how often stuff happens, the period is pi, not 2 pi. So you would do pi over b, not 2 pi over b. Comfortable with that idea? Okay. The rest of the general form does exactly the same thing that it did for sine and cosine. This is a vertical stretch or shrink. We don't call it an amplitude because this graph already goes up and down forever. What does it do? It just makes the graph steeper or less steep. You can't say it's its amplitude. In fact, when we're sketching these things, it'll never even really come into play. Now, it being positive or negative matters. You know, clearly this is the parent function, so that would be positive. If it was negative, this graph would flip over. That is going to phase shift us. So if you're comfortable with this being the single parent function for tangent, you can just shift it around. And then this thing, which we used to call the midline for sine and cosine, is not called the midline for tangent, but it still serves the same purpose. It's the middle of the graph. It's the horizontal line that the graph is centered around. It's not called the midline, but for all intents and purposes, it's the midline. Question for me, what's up?
So when you're shifting it like left and right.
Mm-hmm. Shifting left and right.
Right. So would the vertical asymptote also shift?
Everything about it has to shift, including the asymptotes.
Yeah.
Mm-hmm. And one more thing, I've already kind of mentioned it, flipping this thing up and down. See where it is around this origin? Reflected over the x, reflected over the y. Same graph. Since you get the same graph, if you reflect it over the x or reflect it over the y, tangent happens to be an odd function. It has odd symmetry. I'm not going to test you on that, but it's good to know. Yes, ma'am. Well, think of the quadrantals. From 0 to 90 degrees, 0 to pi over 2 is quadrant 1, right? There's quadrant 1, 0 to pi over 2, where tangent's positive. And then pi over 2 to pi is quadrant 2, where tangent's negative. Pi to 3 pi over 2 is quadrant 3, tangent's positive again. And lastly, 3 pi over 2 to 2 pi is quadrant 4, where tangent is negative once again. So it's literally the same radian measures as the quadrantal angles. For this question, we're just going to describe the transformations. We're going to find some asymptotes. We'll find some zeros. And it says graph 4 periods. Yeek. Okay, well, what do we have? I'm seeing a negative sign on the front. So that's reflect over the x-axis. And this right here, horizontal inside, opposite. Looks like I'm multiplying my x's by 2. So I'm clearly multiplying my x's by 1/2. Horizontal shrink, factor 1/2. This graph was not phase shifted, left or right. This graph did not shift up or down. That means it's going to have the exact same zero, the starting zero. What makes the inside equal 0? Because that'll still hold true like it did for sine and cosine. What makes the inside equal 0? That's where we're going to quote unquote start our graph at the origin. The parent tangent wave has a point at the origin. This hasn't been shifted up, down, left, or right, so it has a point at the origin. However, we do have a horizontal shrink of factor 1/2. So then the period length of this thing is no longer pi. Now the period now is pi over 2. My asymptotes will be pi over 2 away from each other. My zeros will be pi over 2 away from each other, so on and so forth. When I sketch my tangent and cotangent graphs, I don't even use y values because who cares? Here's what we know. Because I didn't shift it, it does still have a 0 at the origin. The period is now pi over 2. That means the next 0 will happen at pi over 2. The one after that will happen at 2 pi over 2, which is pi. And the one after that will be 3 pi over 2. Those are zeros. And you know what happens between zeros? Asymptotes. Halfway between pi over 2 and 0, I said it backwards, halfway between 0 and pi over 2 is pi over 4. This must then be negative pi over 4. So every one of those is a type of over fourth. 1/4, 2/4, here's 3/4, 3 pi over 4. 4/4, 5/4. 6/4, 7/4. Those are asymptotes. The further I went right, the wider my stuff got. Picture not drawn to scale. Go home, tangent, you're drunk. This says, hey, you know all those y values that your tangent should have had? Change their sign. That's what that says. This represented quadrant 1, where tangent was positive, so now it's got to be negative. And then the graph just repeats itself. Ta-da! That's it. That's all there is to that. And as long as you're comfortable with that, we can move on to our reciprocal function, cotangent. Everybody's cool? Awesome. All the same logic is going to hold true for cotangent, and the only thing that changes is, well, the fraction's upside down. So that means everywhere sine is 0 is now a problem. It'll be undefined. Everywhere cosine is 0 is now a 0. So where's cosine 0? All the odd multiples of pi over 2. And now our asymptotes are at all the integer multiples of pi. Positive and negative, of course. Flipping the fraction upside down does not change its period length, though. It is still pi. Everything about the standard function is exactly the same as tangent. Vertical stretch and shrink, horizontal stretch and shrink. It's going to affect the length pi. Phase shifting, shifting up and down of the line that's in the middle of the graph. Oddly enough, not known as the midline, though. Okay. This time I have asymptotes at all of my integer multiples of pi. So that means my x-axis is now an asymptote. And halfway between every set of asymptotes, you will find a 0. You know what? I think this shows up. Go ahead and throw those on there. Now let's talk about which way this graph points. 0 to pi over 2 is quadrant 1. Tangent's positive in quadrant 1, so is cotangent. The only way you're going to stay above the x-axis and get infinitely close to this and still go to an infinity is if you do this. That's quadrant 2. Tangent's negative in quadrant 2, so is cotangent. And then the graph just repeats itself. So what relationship do you notice between the tangent function and the cotangent function? Liam?
They're kind of like the inverse of each other.
When you say, okay, inverse would turn it on its side, but what you mean is that it's clearly been reflected, though. That's what you mean, right? Now, if I reflect it, it will point the same direction, but it's also been shifted. There you go. So if you took a tangent function, reflected it over the x-axis, and shifted it by pi over 2 either direction, you would have the cotangent function. And the same thing is true for cotangent to tangent. Shifted by pi over 2, reflected over an x-axis, there you go. So yes, tangent and cotangent can be written as one another, just like sine and cosine can be written as one another. Cool with those ideas? Stunned silence. Okay. Let us now do with cotangent what we did with tangent a moment ago. Describe some transformations. And this time we're going to graph 2 periods, it says. 2 periods instead of 4. All right. We do have a vertical stretch factor 3. That just makes the graph steeper. But since I don't put y values on my graph all that much, we can just say it happened. While we're talking vertical, we might as well mention that. Shift up 1 unit. Now, it's not the midline, but it is still a line that's in the dead middle of the graph. And most important is this transformation. This is x times 1/2. Looks like I'm cutting my x's in half, so I'm not. Horizontal stretch, factor 2, because horizontal inside opposite. So the period, which is supposed to be pi, is pi over 1/2, also known as 2 pi. That means there will be 2 pi between its asymptotes, 2 pi between its zeros. It has not been shifted left or right. Tangent is cosine over sine. So every time sine is 0, I'm undefined. Ooh, sine is 0 at 0. So this graph's first vertical asymptote is the y-axis when x equals 0. And the next one will be every 2 pi away from there. And that is how we'll figure that out. So let's put an asymptote there and an asymptote here. Clearly between those is going to be where we find our zeros. But wait a minute, they're not actually zeros They're not actually zeros this time, because all of my zeros have been shifted up 1. So they're just the point that's in the middle of the graph. Instead of being on the x-axis at y equals 0, they're now all up at y equals 1. We have not reflected anywhere, so this zone between the asymptote and the 0 still represents our first quadrant. And cotangent, just like tangent, is positive in quadrant 1. So above the middle line, see I called it a middle line instead of midline, and then below. Oh, I forgot to mention, cotangent is odd also, just like tangent is. I just forgot to mention that. Yes.
The period is 2 pi. Why is the asymptote at 2 pi?
No, a period of 2 pi means that there's a distance of 2 pi between the asymptotes. So from 0 to 2 pi, from 2 pi to 4 pi. It also means there's a distance of 2 pi between the middle line intersections. So from pi to 3 pi. Yes, ma'am. Because tangent and cotangent are both positive in quadrant 1, right? The zone between the first asymptote and the first 0 represents quadrant 1. Since we're positive in quadrant 1, we're above that middle number. Oh, the fun stuff. Secant and cosecant. Why secant first? I don't know. It's just what I did. Okay. So secant and cosecant. Secant is the reciprocal of cosine. That means it is very related to the graph of cosine. The only problem is cosine of x has the ability to be equal to 0. That means secant of x has the ability to be undefined at an infinite number of places because it is undefined. When cosine of x equals 0, and we've already talked about where that happens. X is 0 in the quadrantals means you're on the y-axis, so those would be the odd multiples of pi over 2. Because the period of cosine is 2 pi, so is the period of secant. Now let's talk about the zeros of secant of x. Secant of x is represented by this fraction. Tell me, when is the only time that a fraction's value can equal 0? If the top is 0. So when does the top of our fraction equal 0? Never. So there are no zeros for secant of x. By the way, just like cosine, secant of x is an even function, if you care. How are you guys at remembering that cosine and secant are reciprocals? Pretty good at that? Okay. I do my best to not memorize things. So if you asked me right now, quick, where are the asymptotes for secant of x? What I would do is, in my mind, I would say, well, that's 1 over cosine, and cosine is 0 at pi over 2, 3 pi over 2, 5 pi over 2. I don't have it memorized. I know why it's true. Okay? But how would I have pulled it off if it was a much more difficult question? I mean, we're talking shifted left, right, center, reflected, and all kinds of mean stuff. This is how. What I do when I have to graph a secant and cosecant function is I graph its reciprocal as a ghost image. That's what I like to call it. So I'll graph it in pencil as a dotted line. I'm going to graph the parent cosine of x as a dotted line. Parent cosine of x begins at a maximum on the y-axis. Its period is 2 pi, so halfway between 0 and 2, so it ends at 2 pi, and halfway between 0 and 2 pi will be a minimum. Notice my y's go by 1/2. Okay? Halfway between my minimum and maximum, I'll be on my midline, and then repeat the pattern backwards, like this. So this is the cosine wave that is extremely related to the secant function. Because look, every time that cosine wave hit its midline, that's a place where cosine would have been 0, which means secant would have been undefined. Because that's where cosine is hitting its own midline, which is supposed to be a 0 for cosine. Now let's talk about the maximum, the first maximum right here. That's a y value of 1, right? What's the reciprocal of 1? Anybody? What's the reciprocal of 1? Oh, it's still 1? Oh, okay, so that means when cosine is 1, so is secant. But what's the reciprocal of 1/2? Oh, so that means when cosine would have been 1/2, secant would have been 2. What I'm getting at here is it's the exact same shape, but it has to go up instead of down. And I have to get infinitely close to these guys. So you basically take this bell shape and turn it upside down. Is it because you can't see or because you're struggling to understand it? What's the reciprocal of -1? -1. Can we agree that the reciprocal of a negative number is still a negative number? So that means every y value that secant has here has to still be negative because every y value for cosine is negative. So I have to stay negative, but I have to get infinitely close to these lines and go to an infinity. That forces the graph to do that. That is 1 period of secant of x. We might as well throw the other ones on there. I do not have the parent secant graph memorized. I just happen to know how to graph cosine. And I just turn the U shapes upside down.
They go like opposite.
They go in the exact opposite directions, yep. So that's all I do. I graph a ghost cosine, and I turn its bells and cups upside down. And now I have secant. In the exact, yes? Yeah, so you could stretch, shrink, flip, shift, and it would still be the exact same idea. I would graph a dotted line of the cosine that fit that function, and I would just turn all of its cups and bells upside down to get the secant function that matched. And that's actually what I'm going to do in the notes, because I honestly cannot graph secant and cosecant without their reciprocal functions. But it's just one of those things that I learned how to do. Rather than try to memorize a graph, I know why this has to be the graph. Is it faster than memorization? No. But it is much more efficient because I will never forget that. Yes, Alex?
If I shift up enough, will I have zeros or no?
Well, yeah, the parent function has no zeros, but if you do shift it up or shift it down by 1, now it has zeros, but that just is a product of you shifting. Cosecant follows the exact same logic, only now our ghost function is sine. So every time sine of x is 0, this bad boy is undefined. And since sine is 0 whenever there's no y value, aka the x-axis, that's at 0, pi, 2 pi, 3 pi. And just like its reciprocal, cosecant of x is an odd function. What? Somebody said wait. Crud. I didn't mean to write that on zeros. I meant to write it on asymptotes. Sorry. Watch this junk happen. You ready? Ta-da! I had to switch them because I accidentally wrote the asymptotes on the zeros. There are no zeros, just like cosecant, or just like secant, excuse me. And the period is still 2 pi. And if you don't like the arrows, you could just scribble out the word zeros and write asymptotes. Oops. Regardless, do I have the cosecant function memorized, what it looks like? Nope. Do I know where its asymptotes are right off the top of my head? Nope. But I could tell you where sine is 0. Oh, which means I know where cosecant is undefined. So I would just graph a dotted sine function. Sine starts at its midline and then goes up back down to midline, then minimum, then midline. And just repeat the same pattern backwards. There we go. Parent sine wave. And every time it hits its midline, cosecant is undefined. And we're just going to turn its cups and bells upside down, just like we did for secant.
So is that like those two considered one period?
So this is, yeah, that's one period. You have to have all the positive and all the negative values it can attain to call it a period.
So much like the regular sine and cosine.
Yep.
Cosecant and secant are just shifted versions.
Exactly. Secant and cosecant are just shifted versions of each other because sine and cosine are shifted versions of each other. In fact, it's shifted by the exact same amount, pi over 2. Well, you think about it, because it's just a reciprocal, right? It's going to have the exact same numbers in that fraction. They're just turned upside down. So it's still and we think about it like this. It's called cosine because it's complementary to sine. It's called cosecant because it's complementary to secant. So of course they would add up to 90, which is pi over 2. That's why the shift of pi over 2 gives you back the other function. So we are going to skip these two questions for now. We will come back to them because I want to do a couple graphs. We're going to finish these notes tomorrow. But today we're going to get these two graphs on here. We're going to get a cosecant graph and we're going to get a secant graph. And I'm looking at this thing and I'm going to be real with you. I have no clue what that graph looks like. No joke. I don't know. I don't need to know because I can graph sine. So what I will do instead is I'm going to look at the reciprocal function. This way I can get a dotted version of the reciprocal function on my graph. And every time my reciprocal version hits its midline, this thing's undefined. And then I just turn the cups and bells upside down and I'm done. Our reciprocal is y equals -2 sine. All right, we do have a horizontal shrink on our hands here and a phase shift. Oh, and we've been shifted up 1. So what do we have? Our reciprocal function does have a midline. That midline is at y equals 1. And the amplitude of our reciprocal function is 2. So we have a maximum value of 3, a minimum value of -1. My y-axis, as usual, can go by 1s. Now let's figure out what's going on with this x-axis. Remember, all the math I'm doing right now is for the reciprocal -2 sine of yada, yada, yada. Period length is supposed to be 2 pi. Ours is going to be 2 pi over b. Our b value is 4. Oh, okay. The length of this period is pi over 2. That's pretty short. And our important information, meaning midline hits, maximums, and minimums, are 1/4 of the period away from each other, which is a pi over 8. Hey, what makes the inside of my function equal 0? Pi over 8. How convenient that my phase shift and my important points information have the same denominator. Since they had the same denominator, we could just go ahead and let the x-axis go by pi over 8. It will make our lives easy. And since I am going to start at negative pi over 8, I'm only going to do the odd ones just so I don't have to write super small if you're okay with that. So we'll begin here at negative pi over 8. So this is 1 pi over 8. 2 pi over 8, 3 pi over 8, 4 pi over 8, 5 pi over 8, 6 pi over 8, 7 pi over 8. I really don't know how far out to go out. No, it doesn't really matter. I think in the homework it tells you how many cycles that it wants you to graph. So let's just, I don't know. Yeah, I don't want to draw all of them. I'm just going to, I'll stop when I feel like it was enough. Alrighty. The midline for the reciprocal function, y equals 1. I will graph the sine function in pencil because it's not actually there. This is a negative sine wave. Negative sine waves look like this. And we begin that shape at negative pi over 8 at its midline, and that at every pi over 8 after that, we're going to hit a special thing. So minimum, midline, maximum, midline, minimum, midline, maximum, midline. That's enough. That feels good enough. Yeah, that's more than enough to see the shape. All right. Every time that sine function hit its midline, that's a vertical asymptote. And halfway between every vertical asymptote, actually, well, it doesn't even matter. I have cups and I have bells, turn them upside down. Oh, that curve got a little stupid on me. So what did I get? 2 periods? I got 2 periods on there. That'll work. That's good enough. When you're doing your homework, if it says graph 4 periods, just if you can get 2 on there, you're fine. You don't have to follow the directions that closely. If you can get 2 periods of a function, you know what that function looks like. That's good enough. Is that a question back there or just a stretch? Just a stretch. Are there any questions about what I did, why I did, how I knew, anything like that? Yes, sir.
Why don't you, never mind.
Are you sure?
Yeah, it was stupid.
Are you guys comfortable with using a sine wave to graph the cosecant, the reciprocal function? Yes, ma'am. Yes, because negative. She asked if I graphed it negatively. Yes, because this is a negative sine wave, so I started at midline and went down. Because sine is supposed to start at its midline and go up. You spooked me. I thought for a second I messed it up, but no, it starts at a midline and goes down.
I started at the wrong point.
Oh crud! Did you start at positive pi over 8? Uh-oh. Sorry.
No, it's okay.
Hey, you know what? Did you do it in pen?
No.
Oh. Well, I was going to say, you could just scribble out your plus sign and make it a minus sign, and then your graph is perfect.
I'll just erase it.
Okay. Just trying to give you less work to do. Let's get one more done, and then we'll call it a day for today. Oh, we have plenty of time. Secant. As long as you're comfortable knowing that secant is the reciprocal of cosine, and you can graph a cosine wave, you can graph this. Do I know what it looks like? Nope. I don't need to. Really trying to drive that idea home. Just like I don't have the unit circle memorized. I don't need to. I will write the reciprocal function, though. I never try to graph the reciprocal in my head. I always draw it. Always. What do we have? 2 cosine pi over 2. So I do have a horizontal stretch or shrink. That is a shrink. Yep. Okay. First, midline. Midline of this cosine function is y equals -1, and we have an amplitude of 2. Sorry about being so repetitive with my midlines, my amplitudes. I just needed the graphs to be able to fit on the papers. That means we're going to be going up to +1 and down to -3. We can go by ones. We're going to have an interesting period length this time, though, because the period's supposed to be 2 pi over b. Ours is 2 pi over pi halves. Dividing by a fraction is the same as multiplying by its reciprocal. 2 pi over 1 times 2 over pi, bless you, is 4, because the pi's cross cancel. Check it out. Our period length is 4. So our important information, the important points are going to happen every 1/4 of that, or every 1 unit. They're going to be 1 unit apart. And you know what I forgot to write on this top one up here? We said it. We said that negative pi over 8 is where we're going to begin, but I want to go ahead and write that, because that makes the inside equal 0. And I want to do the same thing for this. What makes the inside equal 0? 3. So we're going to start, quote unquote, at 3. Start at 3, and important stuff is 1 unit apart. Oh, we can just count by ones on the x-axis. 1, 2, 3, 4, 5, 6, 7. Let's go 8, 9. Let's see if that's enough to get 2 periods on there, because I honestly don't know. We're going to start at 3. Oh, but we're going to be graphing this cosecant function whose midline is -1. Excuse me, cosine function whose midline is -1. There we go. It's a positive cosine wave. It will start at a maximum. That means at 3, we're at our maximum value of 1. We have a period length of 4. So at 7, we'll be back at our maximum. Halfway between our two maximums, we'll be at a minimum. Halfway between them, we'll be on our midline. That's way more than enough. And everywhere that cosine wave hit its midline, we have a vertical asymptote. So, oh, the x-axis is a vertical asymptote, even though we shifted. Or this is a secant graph, isn't it? Never mind. Secant's not undefined at 0, normally. See, I don't know. I don't need to know. I feel like I went over and above on this one. Went out way too long. Now we just turn our cups and our bells upside down. That's 2 periods. Good enough. I mean, okay, one more. There you go. There. And that is it. Are there questions on how to graph secant, cosecant graphs? We'll practice tangent and cotangent tomorrow. I wanted to get these in your brain because, in my mind, they're the difficult ones. No questions? Okay. Awesome.